Okay. It says we're recording. All right, so we're going to start on chapter 4 today, which is on scatter plots and correlation, okay? So a scatter plot is a visual representation to show the relationship to two variables. We try to put the explanatory variable on the x-axis. So what I mean by that, here, let's get rid of this, is, so we've got a graph here, and we try to put the explanatory variable on the x-axis and the response on the y-axis, okay? Now, sometimes this is a little bit easier than other times. Let me ask you guys a question. I wish we had more people here. We've only got 5 people here. So with me is 6. So do you guys think that a person's shoe size and height would be correlated?
Yes.
Okay. How about a person's time spent exercising and their weight? Do you think those would be correlated? Probably. Now, the question is, let's do the second one first. Does the time spent exercising explain a person's weight, or does a person's weight explain how much time they spend exercising? Should we make a poll here? Exercise explains weight, or weight explains time exercising. Okay, we've only got 5 people here, so you all have to vote.
Actually, can we make an option for both?
Some of these are pretty hard, but this one's pretty good. Who are we doing here? Who hasn't answered? It's Lindsay. You haven't answered. Okay, you're unanimous. Yes. Okay, so generally we would expect that time spent exercising would explain the weight. The weight would respond to that, okay? Now, we might expect, I'm going to just draw a line here, that people who exercise more weigh less. So this is what this would be an example of a negative correlation, okay? Now, I want to do another example. In fact, we'll do it right now. So here's what we're going to do. We're going to collect some data on you guys. Do you think your shoe size and your height would be correlated? What do you think, Jada?
Sorry, kind of cut out. Could you repeat that for me?
Do you think a person's shoe size and their height would be correlated?
Yes.
Yes. Okay. So we're going to do an experiment right now. We're going to find out everybody's shoe size and their height. Okay. So we'll start with Lindsay. What's your shoe size?
8.5.
8.5. And how tall are you?
5'5".
5'5". So you're 65 inches. I'm going to convert it to inches so it'll be easier. Jada, what's your shoe size?
7.5.
How tall are you?
5'7".
5'7", so that would be 67 inches. Okay. Jerica?
8.5 and 5'8.5".
5, 8.5. So you're 68.5 inches. Okay. Cheyenne?
8.5 and 5'9".
5'9", so you're 69 inches. And Christopher?
6 feet tall, and my shoes are 10.5.
10.5. Okay, good. I wish we had more people. I'll put mine in here. I'm a size 12, and I'm 76 inches tall. So y'all are short compared to me. Okay?
I have a question.
Uh-huh.
Wouldn't we want to do like separated genders for shoe size? Because I can fit like 6.5 in men's.
We would, and we should, but we've only got 6 people in our sample size here because where is everybody else? Should give you guys all extra credit for being here. Maybe, well, we are giving you extra credit for being here. They're not getting it, but
That's a good idea.
yeah. So 5 points today for being here on time. All right. So now, so the first thing you should do when you have data like this is you should create a scatter plot. And so we're going to do that right now. And the nice thing about correlation is units don't really matter. Now the question is, should I put the shoe size on the x-axis or on the y-axis? What do you guys think? This one's kind of a chicken or the egg thing. Does your shoe size explain how tall you are, or does how tall you are explain why you have big feet? So this one is a little bit of a chicken or the egg thing. We're going to put shoe size down here, okay? Shoe size and height. Okay. Now, in this case, let's see here. So we got 7.5 to 12. So here's what I'm going to do. We're going to put little tick marks here. 7, 8, 9, 10, 11, 12. Seven, 8. I'm going to put them all in 10, 12. Okay, and then our height goes from 65 to 76 inches. So I'm going to go 65, 68, 71, 74. That's probably good enough. Okay, so this is 74, 71, 68, and 65. And the height, we probably should put this as in inches. Okay. All right, so now we're going to take our data here that we just got. Hopefully I can put these side by side so I can kind of see them together. Okay, so shapes. I need a little circle here. So 8.5 and 68.5 inches. So that's about right there. And 7.5 and 67 inches. It's about right there. 8.5 and 68.5 inches. That's about right on this there again. 8.5 and 69 inches. 10.5 and 72 inches. And 12 and 76. Okay, now that's a pretty small data set, right? But what do you guys think? Does that look like roughly a straight line?
Yes.
Yes. Okay. So we could probably draw a straight line through this pretty well right there. Okay. Now we've got a little bit of variation here, but yeah, we could probably draw a straight line in here. And so this would be an example of what we would call a positive correlation. Okay. So when it goes from low to high, it's positive. When it goes from high to low, it's negative. And So this is something you guys can do on a piece of paper. Now, some other things to consider. Let me ask you this question. We're going to ask Lindsay. Lindsay, do you think your weight and your test score would be correlated?
No.
Yeah, that doesn't make any sense, right? And so if we were to draw, for example, another graph here. Let's say this is a weight and this is test score. Okay. And so we would expect that there would be no correlation. You're going to have just a bunch of dots here. Sorry, they're making them big. Okay. And so we would expect this would be an example of, I didn't give myself much room, did I? This would be an example of no correlation. We don't expect any sort of a thing. This is also called a null plot. Okay. And then the other kind of, well, there's a couple other kinds of plots you could see. You could see something that looks like this. Here, I'm just going to draw a curve. I'm not going to draw the dots, but you might see something that looks like a curve. Okay. This would be an example of a non-linear correlation. Okay. So, so these are the main probably 4 types that you would see: a curve, but we're looking mostly for straight lines. Okay. Now, let me show you a couple other things here. So the idea here is we're going to look for striking deviations from the patterns. We're going to ask, is it a strong relationship, meaning are the dots close together, and is it positive or negative? Okay. So the correlation coefficient describes the strength of the relationship of a straight line. It's known as we use the letter R. So correlation, maybe I should do this first. Correlation is always between -1 and +1. A strong correlation, we would say the absolute value would be greater than 7. Maybe I should call this moderate. Moderate correlation would be between 0.3 and 0.7. And a weak, your absolute value of R would be less than 0.3. So close to the ends, meaning -1 and +1, indicates a strong correlation. Close to 0, maybe I should put can indicate no correlation. But there's a couple things that I want to point out here. There's this website here that talks about the correlation coefficient. So the idea, dots that are clustered close together are going to be closer to 1, and then dots that get farther apart are going to be closer to 0. So some examples of this would be an example of no correlation. It's hard to get exactly 0 unless you kind of contrive your data set, but this correlation coefficient of 0.03, you can see there's no real pattern to this data, so this would indicate no correlation. Correlation coefficient of 0.28, you can kind of see that you could fit a line through here. It kind of is a positive direction. It goes from low to high. You can kind of see some parallel lines here. So 0.28, that's less than 0.3. We would say this is a weak correlation. 0.48, this would be a moderate correlation. You can see that there you could fit a straight line through here. It's positively correlated. This would be a strong correlation, 0.72. You can see the dots are getting closer together. 0.89, once again, the dots are getting even closer. This is really close. 0.99, you'd almost wonder if your data was faked because these dots are really close together. So yeah, so that kind of gives you an idea of how the correlation coefficient works. Now, there's an equation that we're going to use, which is down here. And this equation always assumes it's a straight line. Now, it's not always a straight line. Let me give you some other examples here. And this is why it's important look at the scatter plot. And so let's look at this middle line first. You can see these three are all positively correlated. Correlation, it's related to slope. You can see that this one's steeper than these other two. All three of these are positively correlated. All three of these are negatively correlated. The slopes aren't necessarily the same, but these would all be negatively perfectly correlated and positively correlated. Now, the idea here is we're looking at the dots. If they're close together, so 0.8 would be a strong correlation, 0.4 would be a moderate correlation. This is a null plot. Okay, these would be negatively correlated. So positive 1, negative 1 would be equally strongly correlated. Positive 8, negative 0.8, those would be equally strongly correlated. One's in the negative direction, one's in the positive direction. Now, here's the problem. We're going to calculate the correlation coefficient here, which at the end of class here. So we'll go through this. In fact, we're going to do it for the data we just collected. But this assumes that you have a straight line, okay? Now, if you have something like this, okay, you can see that these dots are correlated, but it's a non-linear correlation. Now, this, if we use this equation right here that we're going to use later here, if you don't look at the scatter plot and you get a correlation coefficient of 0, you may erroneously conclude that there's no correlation, when in fact there is correlation, it's just non-linear. These are some other strange looking dots. I would say these are just kind of contrived data, but this is something you would see. You would see a curve like this in real life. So this would be an example of a non-linear correlation. Here we've got a couple of different non-linear correlations. Once again, if we only look at the equation without looking at the scatter plot, you would erroneously think that there was no correlation. This is kind of an unusual data set. I don't know. This looks like you've got 4 little clusters of data. And so anyway, that's why it's important that we're looking at a correlation, at a scatter plot. If our scatter plot looks like this, then we get a correlation coefficient of 0, we would conclude that yes, the correlation coefficient, there is no correlation. Not so with these. So correlation coefficients and scatter plots are related. Oh, Jerica and Lindsay traded places. That's kind of weird. I wonder how that happened. So anyway, so does that make sense on how correlation coefficient and scatter plots are related? Okay. All right. So a couple other things. Oh, actually, so this is kind of a little graph that kind of shows you. I used to teach at BYU Idaho, and this was something they used. They talked about the hot dog shape. You can see this kind of looks like a hot dog. The hamburger shape, this would indicate no correlation, and then the banana. So whoever did this must have been very hungry. It is lunchtime, I'm hungry too. But you can see this is kind of a curve here. So this would be an example of a nonlinear. This is a null plot, there's no pattern, and then the hot dog shape. So couple of other things that we want to talk about. Let's talk a little bit about spurious correlations. This is kind of a fun website. You know, you've probably heard the relationship that correlation does not equal causality. So these are some graphs. This Tyler Vegan, I don't know who he is, put these together. Do you think that U.S. spending on, well, this shows that U.S. spending on science, space, and technology seems to be correlated with suicides by hanging, strangulation, and suffocation. So the question is, we'll ask Cheyenne, do you think when you study science that it makes you want to kill yourself? Are you there?
No.
No.
I don't like science, but
All right. You may not like science, but it doesn't want to make you want to cause yourself to strangle yourself. Okay, so so just because two things are correlated doesn't mean that maybe this could imply that spending on science, space, and technology leads people to kill themselves. I think how about this one? The number of people who drown falling into a pool correlates with the films that Nicolas Cage appeared in. So Christopher, does watching a Nicolas Cage film make you want to drown yourself?
Sometimes, yes.
Sometimes. How about this one? This is a good one. Per capita cheese consumption and number of people who died become entangled in their bed sheets. Do you think that those are related? Apparently they are, and there's a correlation right there, right? Don't eat cheese, Jerica, or you're going to die in your bed sheets.
Probably just population.
Just population. What does that mean?
Just there's a higher population of people, and there's more. What is it? I don't remember what the other one is.
Yeah. So clearly, this says that if you eat cheese, you got to be careful. You could die in your sheets. Do you think those are really related?
No.
Yeah, probably not. How about this one? Per capita consumption of margarine. So if we quit eating margarine, we'll lower our divorce rates. Do people get divorced over margarine, Jada? Or butter?
I would say probably not.
Yeah. So these are some spurious correlations. Oh, this is a good one. The age of Miss America and murders by steam, hot vapors, and hot objects. So we need to keep the Miss America young to lower our murder rate from steam. Do you think that's related, Lindsay? So these are just some silly examples to show that correlation does not mean causality, but there's some weird things. This is an interesting one. Let me pull this one up. Did you guys say something?
Doesn't it also base off of like how they separate the numbers? Because like if you put like the murders one with like the age of Miss America, like if you put the numbers even to where it's like, oh, she's 18 and there was 18 murders, like it wouldn't be correlated.
Well, so this is you said the Miss America. So yeah,
But like 5 murders, like they wouldn't be correlated at all.
Yeah, so 23. Well, this is in 1999. We had age of Miss America was 23 and 3/4, and they had about 7 murders. It looks like in 1999, and again in 2000, again 2001. Looks like those are perfectly correlated. We get a little bit of variation as things go. I mean, these are just silly, and that's the purpose. Is just to show you that these are just silly examples, but correlation does not equal causality. I will show you something interesting, though. In fact, maybe I was going to wait until later, but maybe I'll do it now. This one here. Well, before I do that one, let me show you this one. This is an interesting one. Once again, this is an example of a nonlinear correlation. This one's one I actually believe. So there was a lot of violent crime from the 60s through the 80s, and one of the things that they used was leaded gasoline, and they used lead in paint. And so the crime rate increased as the leaded gasoline increased. And then around 1988 or so, they started using unleaded gas, and the crime rate dropped. Now, this one, lead can cause neurological problems. That's been proven, and so it seems like this one could be a legitimate correlation that when we got rid of the lead, the crime rate went down. So this is, I think this is a good case where, yeah, it does appear that lead and crime are related. Another one that I wanted to show you that I thought was pretty interesting is this Freakonomics one. Now, I know you can't hear, so I'm going to narrate after we get done with this dumb commercial. hurry up. Let's get off of this. Okay, now here we go. So this is Freakonomics, one of my favorite statistics podcasts. Talks about cause and effect, and they give this. This is Captain Kangaroo, who used to be popular in like the 60s, I think. And so he talks about polio. And of course, polio causes you not to be able to use your arms and legs, or your legs mostly. You can see these kids with braces and sitting in wheelchairs. And so back in the 20s, they were trying to figure out what caused polio, and they didn't know what caused it. And so one of the things they noticed was there was a really strong correlation between ice cream, the consumption of ice cream, and how much polio happened. And so this was really a strong correlation. And so people believed that maybe that ice cream did cause polio. So you can see this graph here. These are polio uh, diagnoses. And for some reason, it really spikes in the summer. And oops, well, that's good enough. I meant to stop that a little bit sooner. So you can see here that, yeah, it looks like the green line is your ice cream consumption, and then whatever color that line is your polio. And so it does look like ice cream, consumption of ice cream is correlated with polio cases. Now, is that true? Does ice cream cause polio? No, because if it did, you'd all be paralyzed, right? Okay. So what do you think causes polio? Do you guys know?
Wasn't it a microbe that was in the ice cream? Like in milk?
Nope, it has nothing to do with milk. Anybody know? Jerica's going to pull out of Google here, isn't she? Cheater.
Isn't it just transmitted normally like the flu?
It's not transmitted like the flu. It's actually a waterborne virus, okay? So what was happening is kids are swimming, and adults too, because adults get it too, but people would swim in infected lakes and ponds. And when do you do swimming? You do that in the summer months, June through September, right? That's when you're doing all swimming. What else do you do in the summer? You eat lots of ice cream, right? And so it's kind of interesting, you know, the lurking variable, I guess, is time of year. People eat lots of ice cream in the summer, they swim in the summer, and those two are definitely correlated, but that does not mean that ice cream causes polio. And so this is an example of the kinds of correlations that people think are causal, but are not. Can you guys think of anything that people think are causal that are maybe not today? What about this? What does this cause? Well, the news has kind of gone down on this. What do cell phones cause?
Cancer.
Cancer, brain cancer. Do you guys remember? Okay. How about vaccines? What do vaccines cause? Do you guys know?
Autism.
Autism, thank you. I was almost excited that you didn't know, because that would mean it was bad. Yeah, there was actually a study done that was faked, that used fake data to say that the vaccines cause autism. That guy has been discredited. So yeah, there could be some spurious correlations. So this was one that was really well thought of, that it might be a link. Anyway, let's go back here. All right, I think I've showed you all the good stuff. So now, at this point, How are we doing on time? Oh, we're doing really good on time. Okay, so I'm going to give you this formula here, and we're going to calculate the correlation coefficient based on our shoe size. Now, these steps here at the bottom here, I am not going to give you on the test, but will use them today while we're learning how to calculate the correlation coefficient. This is the formula here that I will give you. If you want to memorize these steps, you can, totally optional. I'm just going to give you this, but do you guys know what X bar and Y bar stand for?
No.
No? Cheyenne knows. Don't you, Cheyenne? Well, I don't know what. Cheyenne sounds like a computer or something. I don't know what that was. Christopher knows.
What do I know?
What does X bar and Y bar stand for?
The mean of the X value and Y value.
Yeah, it's the sample mean. Okay. So we just did a sample of 6 people in our class, and we're going to find the mean. So X bar stands for the mean. What do you think S sub X stands for? Let's pick on Lindsay. Oh, we lost Cheyenne. She maybe should come back.
Repeat the question.
What do you think the S sub X and S sub Y stands for?
All right, so that's going to be 15376.
Sorry, that's my husband, if you can hear him. Would it just be the standard deviation?
That is correct. Okay, so as we're looking at here, so I've got the steps listed right here. So X bar and Y bar are your means and your standard deviations for your X and your Y variable. You can see this looks a lot like data minus mean over standard deviation, right? So this is your Z-score for your X data, your Z-score for the Y data. We're going to multiply those together. This means find the sum, and then we're going to divide by n minus 1. So we're going to go over this, and we're going to find out if the shoe size and the height, if there is a strong correlation here, okay? Now, let me just mention this. There's only 4 people here. I don't know why we have so few people here. What do you guys know? So all of you should have a calculator that can calculate the mean and the standard deviation quickly and easily. Is there anybody who does not know how to calculate the standard deviation with your calculator?
I don't think I know.
Okay. So what kind of calculator do you have, Jerica? A pink one. Is that the TI 30?
Yes.
Okay. So here's how you're going to find out how to do this. So you're going to go to YouTube, and then you say, how do I find a standard deviation on TI? Is it a 30 XS? I think yours is a 30 XS, isn't it?
Yes.
Okay. And you can see lots of videos like this one here or this one here. They're like 2 to 5 minutes that will be easy to show you how to do those. Although yours looks different than those. This one looks more like yours. Yeah, this is yours right here. So that's a 3-minute video. And you can do this for any calculator. If you have a Casio, you can put in the Casio and then whatever model. You can see all the different modules they've got in here, whatever. And so, because I made you guys figure out the standard deviation by hand last time, right? Okay, I won't make you do that again until the final exam. So I'm going to expect that you can enter in the data and get the mean and the standard deviation really easily. You just have to enter the data, and it should show you how. So I'm going to find the mean shoe size. The mean shoe size is 9.25. The mean height is 69.58 inches. The standard deviation, now we're always assuming this is a sample, okay? So don't use population or that'll give you the wrong answer. This is a sample. So we've got a mean shoe size of 9.25, and that varies by about 1.6 shoe sizes. The standard deviation, so we've got a mean height of 69.5 inches, standard deviation of almost 4 inches, okay? So we found the means, we found the standard deviations. Now we need to find the z-score for the shoe size, and we need to find the z-score for the height, okay? Now, so I guarantee, I don't usually do this, but I guarantee you I'm going to give you one of these on the test in a few weeks, okay? So this will be a test question. I'm going to give you some data such as this, and you're going to have to find the correlation coefficient, which is represented by letter R, okay? So we found the means, we found the standard deviations, we need to find the standard scores. Now, it's important that when you do this, you're using your parentheses. And so I'm going to take, so this is basically data minus the mean over the standard deviation. So 8.5 minus the mean, which is 9.25, divided by 1.66. Okay. And then I'm going to repeat that for all of my data. And I know I did that faster than you did, but you guys are going to get fast at this, right? Then we're going to do the same thing, parenthesis, the height minus the mean, and then we're going to divide by the standard deviation. Okay. And we're going to copy that down a bunch of times. Okay. Now, well, I'll keep going. Okay, so we found the means, we found the standard deviations, we found the standard scores. Now we need to multiply. These two z-scores are multiplied by each other, okay? So we're going to take the product, so we're going to take this number times that number. We're going to copy that down, okay? Do you guys know what this means? Christopher, what does this weird looking E thing mean?
I can't remember.
Oh, you don't? Lindsay remembers.
I think it just means the sum.
That's correct. So we're going to find the sum of those products that we just found, okay? So that works out to be 4.59. Oh, let me just mention, when you're doing this on your test, I would probably round to 4 decimals in this column and 4 in this one, because if you round any more than that, like you're gonna, it's gonna cause a rounding error when you start multiplying these together. So go to at least 4 digits on both of these, okay? All right, so we found the sum, and then we're gonna divide by n minus 1, okay? Now my question is, we have to figure out what n is. So is n 6 or 12? So we're going to have a vote. There's only 4 of you. So is my n 6 or is my n 12 in this case? What do you guys think? You can give me a thumbs up. What do you think, Jericho? We're waiting on you. Jetta, I mean. Jetta just doesn't want to answer. Can you hear us,
Yeah, I would
Jetta?
say 6 as well.
Say it again.
It's not coming through on my end, but I would say 6 well.
6 as well. Okay, thank you. All right. So yes, that's correct. So we're gonna divide by, so it's the number of pairs, okay? So remember, these are 6 people we've got 2 measurements, so it's 6 people here. So 6 minus 1. So we're going to divide, in this case, divide by 5, which works out to be 0.918. Okay. So, Lindsay, is that, so that's the answer there. Is that strong, moderate, weak, or no correlation?
Strong.
Strong correlation. Okay. And it's strong because why?
Because it's greater than 0.7.
Okay. All right. So now, okay. So just want to point out here, I want to see all of this work on your paper when you do this. This will definitely be a test question. Probably won't put it on the quiz because it takes a little bit longer. But yeah, you should be able to do that. Let's see here. God, we actually got done faster than my other class. I think we've covered everything. That means you guys get the bonus because I wanted to show this video in my other class. And so I'll narrate here. Abortion and crime, Freakonomics. So they did a really interesting thing. This is about a 4-minute video. So I'll narrate it. Basically, they have this little thing from It's a Wonderful Life. So Stephen Levitt is talking right now. He has a hypothesis that says that basically, if we legalize abortion, it reduces crime, which is kind of a very interesting and surprising study. And so they did a, let's see here. I think they talk about this. I haven't watched this for a while, but the idea here is women who aren't ready to have a baby, if we allow them to get an abortion, then their children won't be committing crimes 20 years later. So they did he compared 2 nations here. Oh, they cut this off. The idea here is unwanted children are going to commit more crime. I'm going to fast forward this. This is a little longer, and plus it skipped a bunch of stuff. One of the problems with this is, stop, let me pause here. So he did a study and he was trying to figure out why, let me back up even more, just a tiny bit. Oh, this is not the right video. Well, I'm going to back up a tiny bit. Okay, they did a study. They were trying to figure out what contributed to crime, and basically the crime decrease. So if we put more people in jails, that counts for 30% of the crime decrease. There were also changes in the crack market that contributed 15%. A good economy, more police, and gun control increase that accounted for another 10%. So if you add 30 and 15 is 45 and 10 is 55. So 55% of the decrease in crime in the 1990s was due to these factors. 45% was they didn't know why crime went down. So he has a hypothesis that he thinks that when they legalized Roe versus Wade, that contributed to a decrease in crime. And so then he kind of gives some things here. I think the one main thing, yeah, this is it. He compared the country of Romania and the U.S. And the U.S., I think it was 1973 that they legalized abortion, that they saw that there was a decrease in crime. Whereas in Romania, I think it was 1968, they made abortion illegal. And these are for men, because men are usually the crime problem. Men under age 25, they didn't commit as much crime, but in Romania, men over 25 committed way more crime. And so basically it's a correlation that he did. And he's trying to make the case. So it's pretty interesting, pretty controversial study that's done. But the problem is it relies on correlation. And as you guys know, correlation isn't always causality. He actually has come up, if you're interested in this, revisited. There's a newer video, this one here. This one's like an hour long though. So I won't force you guys to do that one. But it seems like his hypothesis is working out. So that's kind of an interesting thing. So I'm not here to propose one way or the other. You all have your own moral opinions on that, and that's fine. But it was just a very interesting case of correlation that I wanted to share there. So we're done a little bit early. You guys didn't have as many questions as my other class. So do you guys have any questions you want to ask me about chapter 4? Okay, Christopher, let me ask you this. How confident do you feel that you can figure out the correlation coefficient on a test if I give you a bunch of data?
I think that if I used Excel and I like practice with it on this homework, that I could get pretty dang good at it. And then, I mean, if I can do it on it, if I can do it on Excel, then I can do it on a calculator. So.
Well, you have to do it on a calculator. You can't use Excel on the test.
Yeah, I know. It helps me so I can like when you did it on Excel, it helped me visualize a lot of what was happening. So it really helped me like get it in my brain.
And if we were meeting in person, by the way, let's just talk about coronavirus for a minute. Do you guys think part of the reason why I kept this class online was because I was worried that they would shut down school. Do you guys think they're going to shut down school?
I don't know, but doing classes online is awful.
I agree.
It's the absolute worst.
I totally hear you, but the problem is I can't give you a test in Excel. So that's the sad thing. Well, some of you hate Excel. I'm glad you like it, Christopher, but some people hate it. So you're going to have to do it on paper, and you can't do it on Excel. I wish we could, but the testing center's closed, and I can't. I usually put this test in the testing center, and then you can spend as much time as you want on it. But anyway, so sorry. Any other questions you guys have for me? Lindsay, how do you feel about correlation coefficient? Good. Jada? Good. Jerica?
Ready to give it a try.
Ready to give it a try. Okay. So I will tell you this, my other class, you tell me how you feel, but there's only 4 of you, so you get to decide for the whole class. My other class said that sometimes they feel like they don't get enough practice. Would you guys so I've got the homework, which is going to be due on Tuesday for chapter 4, and I'll have a quiz on chapter 4. I also can give you some more problems in Excel that you don't have to turn in, but you can practice them. Would you like more homework that you don't have to turn in? Yes,
that would be good, I think.
Okay.
Just like yeah.
Okay. So I will give you some more homework for practice on just the correlation coefficient. It'll have the answers on there. Just make sure, the main thing is, and I don't mind, if you want to look at Excel and see how the calculations are, that's fine. But you need to know how to do this on pencil and paper, because I wish I could give you a test in Excel, but I can't, so I won't. Any other comments, questions from you guys? Okay. Jerica, is that your house, or is that like a beach house or something? Because it looks really nice.
It's my house.
Wow, you've got a nice looking house. Cool. All right. So one of my other students was like, yeah, I'm in Las Vegas today, but I'm still here in class. So I thought that was impressive. Okay. Any questions you have for me? All right. Well, I'm going to let you guys go then. And quiz and homework on chapter 4 is due on Tuesday. So we'll see you all on Tuesday.
Thank you.
Thanks. And I don't know what happened to Cheyenne, but hopefully she can watch this video.